somehow will be intersected with several talks that we have these days. One of them is one with the previous one. This is basically related with stochastic representations, and also somehow with what Rodrigo said yesterday. This is about inequalities. Okay, so that's what I will do. And before I start, let me just say something about my connection with the Polish community. And I certainly would like to mention my collaborator, Tomasz Bojdecki, a very good friend of mine, and together with other people from Poland, like Lucas and Virginia, Pasik Duncan from Kansas. So it's very nice to have you all here and have all these collaborations. Okay, let me go now to my presentation. This is the agenda that I want to talk about. I present a motivation of the problem. I would like I hope to be able to give a good motivation of why we are interested in the problem of comparison of differential operators, and we are interested in a very particular class of these differential operators. These are exactly the Isaacs operators and what is called the initial dynamic programming principle. Okay, and the main results are related exactly with this part, with the complex combinations of Hamiltonians. Okay, okay. Let's start with the very basic point. Okay, let me recall to all of you the Faynman-Kac formula. Okay, so the idea for that formula is that we have some probability space, we have some SEE, which has this form, and then you will know the form of the infinitesimal generator of this diffusion, which will have this form. Okay? Okay, now, from this point, we can now ask for the stochastic representation of the solution of this Cauchy problem. And we all know that the solution of this problem under suitable conditions on this terminal condition, T is the horizon time, okay, fixed. Okay, so then the stochastic representation of the solution has this form, as the expectation of the terminal conditions at the end of the position of the stochastic system that I represent. Okay, well known results. Faynman-Kac formula. And let me write the previous infinitesimal generator, this one. I will put it in another form. It's exactly the same, but more convenient for me. So I will put it in this form. Okay, this is the drift, this is the diffusion, etc. This is a matrix. Okay. And then, now let me introduce a second generator. Okay, so I will have another functions v tilde, sigma tilde, and then I introduce another operator with the same terminal condition G. Okay, so then, of course, we can go back to the Cauchy problem and get the two solutions, B and B tilde. Right? Good. Now, suppose that we can have this type of inequality, this type of relation between the two infinitesimal generators, okay, for all the T, X, P, and N, okay? And then I will define this complex combination between these two differential operators, okay? So P is some function that depends on time and the position of in the space, okay, which goes to 0, 1, and then I define this other differential operator, A super P, okay, just the complex combination of these two operators. Okay, question. Which is the stochastic representation of the Cauchy problem for this differential operator? That's okay. Well, then, of course, one can write down the Cauchy problem. This is the analogous Cauchy problem. Okay, and well, I will not give here the answer to this question. I present a more general response with the more general differential operators, but this is basically the motivation. Okay, so we are looking for a stochastic representation for a complex combination between two differential operators. Okay. Okay. Now let me move to a more general class of differential operators, and these are the Isaac's infinitesimal operators. And these operators correspond somehow to the infinitesimal generator of a nonlinear semigroup. Let me say some words about that. Okay. So suppose now that we have two compact metric spaces, U and V, again, and then, I mean, what I have here within the brackets is what I had before, right? Now I am introducing these couple of sets, U and V, and I'm defining H plus and H minus. Okay? So these are these are named the Isaac's infinitesimal operators. Okay? And these two operators have some important characteristics. Okay? Now I'll try to. Yes. In this one? Or here? Okay. This is that? Yeah, this is like, where is Q and V? That's the question. Okay, that's what I was about to say. Because exactly, the B and the sigma now depends on U and V. Okay? So, and here, this B, this sigma will depend on these parameters here. Okay? And the same here. So, this, now I'll change a bit the dynamics. Okay? Now I will make the drift and the diffusion term to depend explicitly on some processes that I will be more concrete in the next slides due to T and B. Okay? Now, this system can be thought as something that is controlled by two opponents. Okay? So let me describe that as two. We have two guys, two players, and they have opposite goals. Okay? They have some specific end that I will talk about. But let me stop in something very specific. This is an example of where we have this type of inequality. And it's very easy to check that H minus, that we define here, is always less or equal H plus. Okay? And this is always fault. Okay. Then, let me make some remarks about this inequality. Okay? So, when the above inequality is sharp, then what is happening, and I'll try to be more precise, intuitively an advantage of one of the players is described. Okay? And the other point is what happens when we have the equality between H minus and H plus. Okay? Then this is known as the Isaac's condition. Okay? And in this case, we hope that there is no advantage of one into the other plane. Okay? But this has to be formalized. This is the intuitive part. Okay? Now, I should say that the precise definition of the stochastic game associated with these Hamiltonians, you can find different descriptions of these stochastic games associated with these Hamiltonians. What is the behind? What is in the bottom of the problem? The bottom of the problem is that you can describe the information available to each player in a very different way. Okay? I'll talk a bit in the future slides about this point. Okay. Now, but this is related to this point. The absence of a specific model for the structure of the information available makes this problem challenging from my point of view. Okay? Now, let me give you just a flavor of the type of strategies that we can have. Okay? So these are, we can have this type of strategies, for instance, Elliott-Carlton formulation. We can have feedback strategies. What it means is that you have each one of the players can only see the path of the state of the system. Okay, this is what is happening, the history of the path. Okay, and we can also have randomized structure strategies with information structure like this one. Of course, we can have a more general criteria. Okay, we can add. When I started in the motivation, we only had this terminal function g, but of course we can add some extra function h, which represents the running cost between the initial point, sorry, this should be t, up to capital T. Okay, so in other words, we can generalize. Okay, let me describe a bit the Elliott-Carlton strategies. Just to give you a flavor on how the information can be described between the players. Okay, so we can start with a canonical space, the usual algebra, the linear measure. So I will define this couple of sets, m sub t and n sub t. Okay, these are processes which are progressively measurable. Okay, as well as these ones. Okay, so what is the Elliott-Carlton strategy for the minimizer player? Well, it is a function that will take an element from this set to this set, and such that if these two elements are almost equal in this piece of time, t and s, then the response of the player using beta should be almost the same, okay, in this piece of time. Okay, then we can describe this set as the L. So, in other words, what I have u and the response is some function beta. That's what I'm saying. And then, with this set, then we can define the value function, which the Elliott-Carlton value function, which is the sub of this j function that I defined before. The sub takes here, I take a u here, okay, and then this is the response of the other player that is minimizing, okay, and it's using this function beta. Okay. Now, what is the relation between this function here and the original Hamiltonian that I was talking about? Well, in order to do that, let me describe a bit the dynamic programming principle, which will have this form. These are the value functions that I introduced before, okay? And this is the same value function evaluated in a different time, tau, okay, between t and capital T. Okay, so in the deterministic case, it means that when sigma is equal to 0, the dynamic programming principle implies that the viscosity solution, that B will be a viscosity solution corresponding Isaac's equation. Okay? Now, for the stochastic differential game, this implication is not quite straightforward and requires a lot of work, in fact. Okay? This is related with the initial work, which I will talk about. So these are the semigroups related with the DPP, the work of Nietzsche. So as you can see, so this semigroup that I will introduce basically takes some function phi in this set, and then I can define this operator, okay? The integral from 0 to tau, the running cost times the function phi evaluated in the terminal position at time tau, okay? Then what we have is that, and this formalized somehow, the idea, this is of course a nonlinear semigroup, okay? This is not a standard one. But still we can keep the idea of the infinitesimal generator, of course, and then we can take this limit, okay? And then what happens is that it can be proved that the limit that the infinitesimal generator exactly corresponds to h minus, okay, with this formulation. This is what I introduced before, right? This one. Okay. Now, some remarks. Of course, you can have a similar derivation for the other Hamiltonian, H plus, okay? And for the case that I introduced, the intuition behind is that this is what is called the lower equation. The player has some information priority of the game. Now, this information priority in continuous time is very hard to make precise, because you can imagine you have two guys playing against each other. What exactly means that you can see what the other player is doing. Okay? In discrete time there is no problem to do that. But in continuous time you can leave it just an intuitive argument, right? So this information priority, this is somehow the idea, okay? And well, for the upper Isaacs equation, when we have H plus, we can, of course, have the opposite meaning. Okay. Now, let me go back to the original problem, okay? So, remember that we have the differential operators, okay? H minus, H plus, and we wanted to understand what is happening with the complex combination, okay? So this is the formulation. This is the problem that we wanted to study. Provide a meaningful representation of the unique viscosity solution of this PDE. Okay? This PDE is, this H super P is a complex combination between these two Hamiltonians that I introduced. Okay? And here, this function P is quite relevant, of course. We can think in a simple case when P is independent of the position, okay? Or when P depends only on time, or when it is constant. Okay. So this is the problem then. Provide a stochastic representation for the solution of this P. Okay, some considerations. What we had in mind is that the representation that we will look at should naturally come as a value obtained from playing a formal game. Okay? So we understand that the game is behind that representation. Now we should describe that game. Okay? And then this means that we are looking for a model of rules of the game and strategy such that the resulting game has a value, and this value is exactly the solution of the PDE, of this PDE. This work is based in, of course, there are many people that have worked with specific differential games. In this book, the Russian team is described in this book. Many interesting results. There are also some work that I have done with Wendell Fleming, and this other work by my collaborator Silver, where that uses this type of strategies. Okay. Now I'll give you the heuristics of the representation. Okay, to represent B super P. This is the solution of the problem. Okay, so we can consider feedback strategies. Feedback strategies means that at each time that we fix T, okay, then both players can observe the full path of the process X. And suppose that for each player, this information is available, okay? And then, what is going to happen in the second step is that somehow there is a randomization process, okay, represented by P. So P will represent that we are tossing a coin, okay? So it means that at this time T, the state shifted. At this point, at this X, then we will toss a coin, and with these probabilities, okay? And then this step is quite important. The result of this random randomization, okay, then this will give me a priority rule. So if the coin turns H, then it means then at this time T, B will see what the other player is doing, okay? And if the coin turns T, then the other way around. So we're having like a symmetric game, okay? So if we have the result, then one of the players will have advantage, okay? In the other way, when coin turns T, then we change the rule. Okay. Now, what is interesting to look, and that's where all this intuition comes through, is that when we look at the Isaacs equation, the Isaacs equation is this one, okay? And we look at the form of the Hamiltonians, then what we can see after some analysis is that locally there is a game. And that's what is described here. This is what is described, okay? It's just that we have a local game between the two players, okay, that should result in this value, this super. Okay. Now, what we don't have is the formalization of in continuous time. The way that we approach the problem was using some time discretizations. Okay. In time discretizations, then we can make the above ideas rigorous. I mean, what I just mentioned was the intuition. But the way to make it rigorous requires that we have some partition of time, we discretize the time, okay, the horizon between S and T, okay, we have all the setting of partitions, and what is happening is that what we have is something like that. So we have 0, we have T, and I take some partition. And then, when I imagine that I'm choosing the coin, okay, then I get some marks along this. I put some marks, okay. If it is H, I put here 1, or 0, or 1, or 1, okay. So this gives me, when I'm tossing the coin, then I get some marks. So instead of H and T, then I have 0 and 1, okay? And then you can imagine all the possible paths that I can have, all the possible marks. Okay, I'll show you how the deterministic case is solved. And the stochastic one is more involved, and this is somehow more intuitive for the purpose of the presentation. So the rules of the game are set deterministically, and what I'm saying is that they are known in advance. Okay? So you fix the marks, and then you evaluate what is going to happen with the rules that I described before. So if the mark C sub k is equal to 0, then the interval between this piece of time, okay, here you first see players B actions. So this one has some advantage. That's what I'm saying. Okay. So this part is describing how the advantage of one player, the advantage that one player will have depending on the mark that we have in that period of time is okay. Okay. describe what is happening when C sub k is equal to 0. So we just make the analogous argument giving the advantage to the other. Okay. This can be formalized using these functions. Okay, a super k, which depends on the whole trajectory. Of course, you will be solving the SDE in each piece of time. Okay. Okay. And then you continue on each along the time, solving, taking the decisions in each piece of time to complete the trajectory. And then, with these rules that I mentioned, okay, then we can define a value of the game. Of course, this value of the game will depend on the partition and the marks that we are fixing from the very beginning. Okay? Let me describe or formalize the type of strategies. This a full strategy, for instance, for the player view, will contain a sequence of functions, okay? And if the mark is equal to 1, then what this represents that this player you can only see the information of the previous player up to time tk minus 1. While if the mark is equal to 0, then you will have an advantage of the information of the other player. Okay? Okay, so this is the more general class of strategies. Depending on the mark that we have, we can, of course, construct another set of strategies like the feedback strategies. These feedback strategies means that they only depend on the, if C sub k is equal to 1, they basically depend on the information of the state processes. That's what it is saying, okay, in either case. Here, when C sub k is equal to 0, then I am allowing the controller to depend, to see what the other player chooses. Okay. And then we have three different sets of strategies. We have a similar set of Markov strategies, okay, with the same ideas behind. And then, with these sets of strategies, then we can define this functional, which is similar to the original one. Okay, this depends, of course, on U and D, and on the mark, and on the partition. Okay, that I had, and then doing some calculations, then I got this set of inequalities. This is the relation between this value function, so I can introduce the b minus the lower function using Markov strategies, the lower functions using the general class of strategies, and the upper value functions using this general class of strategies, and finally the value functions when I restrict to Markov strategies. Okay, and this is the relationship between all these value functions. Now, okay. Now let me describe the results basically. Okay, and it can be written in this form. Okay, so under suitable conditions on P is the function that I'm having. Okay, then the Isaacs type equation. This is the Cauchy problem. Okay, has a unique bounded continuous viscosity solution P, which is the limit of these value functions that I described before. Okay, this is the main term, and well, we can put it in mathematical terms, which means all this. Okay, and then, of course, then the idea is to pass through a limit. Okay, when the partitions, when the measure of the partitions is going to 0, and that's it. Okay, then we can approach the P, and we are going. Okay. Let me just describe briefly the main steps. I will not give you the proof, of course, but let me just mention some words. Of course, what is a key element of the proof of this result is the relation between these sets of strategies. But there is also well, it was like a key ingredient to solve this problem, and it was related exactly with the existing results which are based on the Perron's method, and it was originally introduced by Ishii in 1987 for history of first order, and then built usable sets of viscosity sub and super solutions for the SXPT. Okay, some extensions, of course, should be done. It is done, in fact, in the paper. It's when we have a random change of rules. Okay, this is very interesting because the random part comes here, right? Because X is the state of the system. Okay, and well, this is just the information for you can find the result that I talk about. Archive now, and well, thank you very much.